Thank you for the introduction. Good afternoon, everybody. My name is Maarten Heres. I'm working as a PhD at the Technical University in Eindhoven. I'll be talking about in vitro and in vivo dynamic blood volume measurements with photoacoustics. So photoacoustic is a very promising tool for the assessment of perfusion-related parameters, such as vascularization and blood volume. And in the skin, this can provide us with diagnostic value in numerous conditions like skin cancer and burns, but also in skin diseases like scleroderma, which is hardening of the skin, and dermatomyositis, which is an inflammation of the skin. In those two last diseases, the vascularization of the skin is related to the disease activity. And that's why we are interested to investigate the possibility of using photoacoustics as a diagnostic tool. So we are also part of the full phase project that is extensively mentioned in the previous talk. We are working with a probe. I will keep it short about that one. It's a handheld probe with an integrated diode laser. So our goal is to do preclinical validation of photoacoustic imaging, focusing on skin and muscle perfusion. With photoacoustics, you don't get a real velocity parameter normally, but what you do get is information on blood volume and vascularization. And that's the focus of my work and also of this presentation. So the work that I will be presenting is split up in 3 parts. We did a phantom study, also an in vivo measurement on changing blood volume, and I will conclude with in vivo 3D photoacoustic scanning. So first about the phantom study. The aim of this study was to investigate whether we could measure an increasing blood volume using photoacoustics. For that purpose, we developed perfusion phantoms, which are cylindrical gelatin phantoms within a mold. And by using very small needles, we can create channels inside those phantoms. We create 4 different phantoms with an increasing amount of channels. So we increase the amount of blood volume in the tissue, in the phantom, ranging from 0.9 to 3.5%, and the channels have a diameter of 180 micrometer. So we can connect those phantoms to a flow setup and perfuse them with a blood mimicking ink solution, and we set a flow speed of about 20 millimeters per second. And now we can obtain cross-sectional images using photoacoustics of those phantoms. And we can scan over the phantoms to get 3D images. So I'll show you first, this slide. It's about the image acquisition. We use power Doppler to verify our photoacoustic images. We use a different probe for the power Doppler ultrasound measurement, but it has the same acoustic specifications. For image processing, we use an average of 40 frames. We threshold our image based on the background noise, and we also filter using the system point spread function. So those are 3D images of the perfused phantoms. You see the channels in horizontal direction, and you see an increase of the number of channels. We do our analysis, however, on the cross-sectional images, which you see on the left. In the upper row, you see the raw photoacoustic image. On the lower row, you see the selected perfused area of the phantom, the filtered signal. And if we now measure the amount of signal area in this phantom, you see that it is directly proportional to the real perfused area. However, in the most perfused phantom, we see an overshoot of the signal, probably because the channels are interconnecting there. So this is the verification with power Doppler ultrasound. Again, on the left, the top row, you see the raw power Doppler images. On the lower row, you see the filtered power Doppler signal. And again, the signal is directly proportional. The amount of signal is directly proportional to the real perfused area. And we see the same overshoot in the most perfused phantom. So now we are going to in vivo measurements in which we want to investigate the same, whether we could measure blood volume changes. We did that with a 4-minute during measurement on the lower arm of a volunteer, scanning cross-sectionally with photoacoustics. And during the scanning, we occluded the blood flow in the arm for 1.5 minutes using a pressure cuff around the upper arm. So these are typical images that you obtain during such a measurement. On the left you see the raw photoacoustic image. Next to it, the plane wave ultrasound image taken with the same probe at the same location. Next to that, an overlay of the photoacoustic signal on the ultrasound image. And you see that we obtain signal from the skin, that's the upper lines, and under that you can see signal from a vessel. On the right you see a power Doppler image which verifies that we see a vessel over there. If we now take a look at the signal intensity at the skin, we see that the average intensity decreases when we occlude the arm at around 1 minute, and it decreases and it returns back when we release the pressure. Also in the vessel, if we look at the average intensity, we see this phenomenon. So it suggests that we can measure changes in blood volume here. However, we found that those signals are very much affected by motion of the skin and also by the change of orientation of the skin relative to the probe. So that makes those measurements quite unreliable and hard to reproduce. So we thought it was good to go back to a more sophisticated way of scanning the skin. And that brings me to the last part of my presentation, which is the in vivo 3D scanning. We connected the probe, the full face probe, to the translation stage, a 3D translation stage. You see that one on the left. So with this setup, we can do a more sophisticated way of scanning larger areas of skin. I will give you 2 examples of measurements that we did with this probe and with this setup. First one is on the skin of the thumb. In this part, we can also visually inspect and check for any vessels. So we scanned an area of about 2 square centimeters. And what you obtain is these kind of cross-sectional images in which you can clearly see a signal from the skin as an upper layer and a signal from a vessel underneath. If you now combine all those cross-sectional images, we end up with a 3D volume, which look like this. You can see the skin and underlying interconnecting vasculature. Another measurement is taken on the wrist. Also again, an area of about 2 square centimeters. And you end up with this kind of vasculature with and without skin. So with this setup, we can perform a controlled scanning of the skin, visualize the skin, the epidermis, and underlying vessels. So this brings me to my conclusion. In vitro, in the phantom studies, we were able to detect blood volume changes in the physiological range using the photoacoustic probe. And also in vivo, we were able to visualize skin and vasculature with this probe with an integrated diode laser. For future work, we will start with clinical trials on skin diseases to detect any abnormalities and vascularization. And with the multi-wavelength probe that has been mentioned in the previous talk, we can also start to do oxygenation measurements, hopefully. Thank you for your attention.
Great, thank you very much. Thank you. Okay, all right, great, thank you. So just a little advertising for Union College. Those of you who don't know, we're a small undergrad-only institution in upstate New York, about 2,000 students. And so here's a nice shot of campus at the fall. It's a nice time. Not so much in the winter, but in the fall, it's a very nice time. Okay, so photoacoustic microscopy. Most of us probably know that blood is a very strong optical absorber. So if you want to image something besides blood, you need to go at longer wavelengths, as mentioned in some of the previous talks. And so you can also use some contrast agents like ICG or gold nanorods. But as far as, how do you get light at that wavelength? So as far as conventional methods, right, dye lasers, OPOs, they tend to be big, bulky, expensive, and fairly low rep rates. So for microscopy, right, we're going for higher rep rates, and the pulse energy is not as critical. So the approach that we're taking is to start with a compact high rep rate pulse laser and use nonlinear fiber optics to create new wavelengths. And then you can use a tunable filter to pick whatever wavelength you want. So as far as this wavelength generation mechanism, one way to do it is to use a stimulated Raman scattering. So this describes when a laser pulse interacts with the vibrational modes of the material, like in the glass molecules in a fiber. And so that produces a series of frequency downshifted lines. And so what happens, as an example, is that if you send 532 nanometer pulses through, let's say, 50 meters of single mode fiber, is that you can produce, in this case, a dozen extra wavelengths. And so that works well. But the question we were thinking of was, could you use, let's say, a multimode fiber to produce new colors for photoacoustic microscopy? And one advantage is that they tend to be cheaper than, let's say, the polarization maintaining fiber used for this example. But perhaps more important is that the larger cores may lead to higher power handling, so you can potentially scale to higher energies. So just a quick review of fiber modes. So single mode fiber, your core is typically like 5 microns in diameter. And so the single mode that you get, one way of the notation is this LP, linear polarization mode, LP01, right? So the 0 is the azimuthal, right, along the angle, and then the 1 is for radial. And so the actual intensity distribution is very Gaussian-like. Now, if you make the core a little bit bigger, let's say on the order of 8 to 9 microns, then you can fit a few higher order modes, right? And so in this case, you would, let's say, have 4 LP modes. And so the actual intensity distribution has a more of a lobed structure, right? So the question is, all right, if we have some modes here, how do they produce new wavelengths? And so it turns out that 4-wave mixing actually is quite prominent in this situation. So one form common in fibers is degenerate 4-wave mixing. So that describes a case where you have 2 input waves that are the same frequency or the same wavelength and same K vectors. And so they interact and produce 2 more waves of different frequencies. Typically, they're called the signal and the idler. Now, in order for this to be efficient, though, is you need phase matching. So this is a parametric process. So basically, your wave needs to travel at the same speed down the fiber. Unfortunately, if you start with 532 nanometer light, glass has a very strong dependence for the refractive index on wavelength. And so you're not going to get phase matching by itself. However, if you actually have your 2 532 nanometer photons propagating in different modes, it turns out that it is possible for the dispersion between different modes to cancel the effect of the dispersion in the refractive index. So the overall effect is you actually do get phase matching, and that's quite a happy case. So we're basically leveraging that, and so then you can actually develop your sidebands, and they can grow in intensity and actually create more sidebands, and eventually you can actually get a continuum, all right? So for our experimental setup, we start with a Q-switch laser, rep rate's 20 kilohertz, pulse energy is about 15 microjoules, and duration is about 1.5 nanosecond. We send it through about 100 meters of SMF-28 fiber, so this is pretty much the industry standard for telecom applications. It's single mode at 1550 nanometers, but again, we're operating at 532, so that smaller wavelength means you get a few modes in the fiber. And so through four-wave mixing, you create a whole bunch of new colors. And so then we could, or we do, send it through an optical filter to get whatever wavelength band that we want. So if you measure the spectrum coming straight out of the fiber, it looks something like this. So you have your initial 532 here. You got a few discrete lines due to stimulated Raman scattering. And then you get this broad continuum due to four-wave mixing. So it's peaked at about 725 nanometers. In terms of energy, if we picked a filter that let through anything greater than 750 nanometers, you get about 1.3 microjoules. Or if you picked a short pass filter, and so anything, anything, let's see, that was quite the, as you can see here. Oh, it's back, great. And so then if you have wavelengths shorter than 700, you have about a microjoule of energy. And so the extent of the spectrum does depend on the strength of your input, as you can imagine. And so if you vary the input energy, so shown on the bottom here is the maximum case. And so then as you work your way up through this plot, obviously if you have smaller and smaller inputs, you're going to, okay, we're having some technical difficulties here. Let's see if, am I using this laser pointer incorrectly? All right, or do I have to do some magical laser pointer action? Am I pushing the wrong? I don't know. It's only like, okay, all right, it's back. Maybe I am using this laser pointer wrong for some reason. Anyway, so if you have smaller input energies, right, then you're going to generate fewer wavelengths, right? So this characteristic slope is what you would expect from something like from a nonlinear optical process. Okay, so as far as the spatial modes coming out of the fiber, at the shorter wavelengths, you get some structure, right? All right, I hardly pressed anything in that case. All right. Okay, all right, this is very interesting scenario. Yeah, that's right. I should do the photoacoustic mode. All right. Maybe I just won't breathe on that cable, then maybe it'll be okay. Okay, all right. I guess I should just talk really fast until it disappears again, but all right. Let's see. All right, let's try. What if I do that? And that, of course, had, okay, that's promising. Or should I just stick with that? Try again. Okay. Maybe the laser pointer is bad. All right, so we'll just see how long this lasts or doesn't. As far, and it didn't. Okay. All right. All right, let's see. Is that better? All right, maybe we'll try that. No, that didn't work either. Okay. Well. Or maybe should I turn around those monitors on the stage and everyone can watch watch those. Okay. Let's see. Maybe, I'm not sure. Yeah. Seems, or maybe it's the cable on the other end. Okay. Okay. All right. We'll try this. All right. Okay. Oh, you know, maybe it's. You think it's the laser pointer having some weird effects? Okay. Maybe I should not use the laser pointer then. I was joking about the pointer, but that could be the actual problem. Okay, all right, let's try the mouse. Okay, all right, let's try the mouse. Thank you. All right, let's see how this goes. Okay, so as far as the actual mode structure, right, you kind of have a donut shape. That's characteristic of a higher order mode for shorter wavelengths. But then at the intermediate wavelengths, you actually get some better behaved looking mode shapes. And what was somewhat surprising is that at the very long wavelengths, around 800 nanometers, you get very well-behaved modes that look almost Gaussian-like. So indeed, If you were to try to fit a Gaussian to, let's say, the 800 nanometer profile, it fits quite good. Of course, what really matters, though, is image quality, right? Spatial resolution. So if we actually image USAF target, so we chose 3 different wavelength bands and then do the usual like edge spread function and the derivative to get the line spread. So as far as the full width half max of that's how we define our resolution. And so we end up with these 3 cases. So at the shorter wavelengths, that I will not try to point out with the laser pointer, the resolution is clearly not as good. It's about 13 microns horizontally, 12.5 vertically. So again, that's actually not that surprising that it's worse because as we saw before, the actual spatial modes were a bit more complicated at the shorter wavelengths. Meanwhile, for the longer wavelengths where you have a Gaussian-like beam is that you can focus much tighter and get better resolution. Either way, though, the resolution is quite good. So as far as an actual photoacoustic experiment, this is the usual optical resolution photoacoustic microscopy system. So we got some scanning mirrors and we focus the beam into the sample. And so as far as the setup, we focus the light into the sample. In this case, we just have dye-filled tubes, right, 250 micron inner diameter. And then we have a 25 megahertz transducer for detection and an amplifier. And so again, as you scan the laser, right, you acquire your signals. So if we use all the wavelengths, right, then we can see both tubes. So the left one is IR 820 dye at 200 micromolar, and then the right side, the right tube is a red dye. And then if we use a long pass filter, then as you would expect, we indeed only see the left tube where the IR 820 is filled. And then if we just use a short pass filter, then we see the red ink tube. So basically that's just to demonstrate, right, the ability to pick the different wavelength bands. Oh, I'm 2 slides away. All right. Oh, it's back. Okay, great. All right, so as far as trying to scale to higher energies, right, larger cores possible? Maybe not. All right. Let's see if, okay, it's back. So as far as, maybe the higher number of modes in the larger core fiber can lead to increased 4-wave mixing. But when we actually tried that experiment, it turned out with the larger core fiber that we did get a continuum, but it didn't extend very far in wavelength, so about 650 nanometers. So therefore, in the end, probably what's happening is that if you have too many modes, then you have just too many channels. And so therefore, your energy tends to get diluted in one sense. So you can't get high enough wavelengths through this process. And maybe the next one will show up. Her. Okay, I guess I'll just keep going. So then the next. Right. All right, I'll take it. That looks great. Thank you. All right. And maybe it's just my presentation that's causing the problem for whatever reason. All right. Well, let me try to show the full slide, and then I don't have to press animation anymore. All right. I guess I'll just sort of give the conclusions. Basically, is right. We had shown that as far as using a multi-mode fiber, just a few modes, that yes, we can actually create a good range of wavelengths for photoacoustic microscopy, but as always, we're trying to scale to higher energies. And one way we're going to do it is to actually explore polarization control, because we found that if you use polarization maintaining fiber, that has a huge impact on the range of wavelengths you can produce. And so that's basically what we're going to try to investigate. And I would acknowledge my funding source, since that's usually pretty important, but I can't do that right now. So thank you for sticking around.